a great opportunity to be here. I have been enjoying my visit, and I hope that it would initiate the further works together and to continue this joint project and so on. So today I want to speak about mobility and epidemics, how they interact with each other, how they impact each other, and so on. So that's the idea, to see from two perspectives. So first part of my talk, I'm going to focus on that, to see how epidemic impacts mobility. We had some sort of data, and we wanted to learn about that, how during pandemic people reacted to the pandemic, and they changed their mobility pattern. And here you can see all the details of this paper. I just try here to give you the overall picture, what from, let's say, physics perspective, people usually look at data, how they try to understand some patterns and get some information from those types of data that they have. The data set that we had was safe graph data. And as you can see, this is a US map. We had the data of Washington State, and we had the visits of the people to the parks. So these are the parks, either small or big, but these are the visits of the parks. So their mobiles basically were detected whenever they were visiting any park. So we knew who from which district of the town has visited which park in which district. Yeah, that's basically the data. Data was totally anonymous, so we didn't have any access to any further data. So that was basically the data that we had. So here,
people who voluntarily participated in this?
no, it was not voluntary. They just they were monitored by this time. But what we had available, so we had no information of any single individual or whatever. We just had those who have visited. So here, this is a law, gravity law, in different contexts, let's say. So what we see here, this is Tij, so number of visitors from census block group I who visited park J. So more or less, this is similar to the mass of population that we had in I, from visitors that originally were living in that district, let's say. And more or less, this is similar to the mass population, let's say, that you had in the number of visitors they visited that park. So that's why it's named gravity, because usually you can see that there is some sort of proportionality for such kind of amounts of visits and so on. And then here you have the distance between those districts. And alpha is here. So it's not exactly 2 or whatever. So this can be changed. So it's some sort of generalized gravity model. And you have some other factors, renormalization factor, let's say, that for physicists is common. They put whatever they are not interested in, they put it in one renormalization factor or whatever. So it's a common practice for us and so on. But you see why it's named gravity model, because more or less it's the analogy, you can see that it's really similar to that concept. So what it means, if I have log-log plot and plot things versus the distance, I'm going to see a slope. And that slope is the alpha, which shows me that what's going on. So look at that data. So as we said, this was the data. This is the map of the Washington State, latitude, longitude. And the OI, you see that how much is the density of population, let's say there. And then you plot in the x-axis the distance between the different districts of the town. And then you see how many visits I had and so on. So you can see that if you have it till approximately radius of the Seattle, you can have a good fit, which follows that one and give you the slope of that line. So this slope gives you some information. You can imagine that if you're gonna see it again, if you have this line, so if it changes, the slope gonna change. So it means that you had more weight for longer distance or shorter distance. So you have some idea how statistically the mobility pattern has been changed. Yeah? So basically that is the point we wanted to follow. So what we learned when we looked at that. So we compared the data during 2020 versus 2019, which was pre-pandemic, to see that if we make this comparison, what we can learn. First of all, it's important to know that, as you have seen in the previous plot, the gravity model was a good fit still there, which was not trivial at all, a statistical point of view. While the gravity model was already observed and was reported that it's a good match for the mobility patterns of the whole data, whole mobility pattern of the town. So people in the town, they are moving for different reasons, to visit parks, to go to the shopping mall, to go to work, to go back home, and so on. So people had tested this law, let's say, in different resolutions in different cities and so on, and this gravity was still a valid law, let's say. However, here, please note that we only had the visitation of the park, which means it was a subsample of those data. And it does not guarantee that you can exactly have the same law still. You may end up to something else because your sampling strategy might have bias towards something, so you may change the statistics, let's say. But the first observation here, which was important, was that gravity model was a robust pattern, and even though we had only sub-sample, which was the park visitation, so we could still see that. However, the slope may change with different filtering. What means different filtering? We continued subsampling to see what's going to happen. So we sampled, for instance, data for different seasons, cold season and warm season, to see that, okay, is there any difference between the mobility pattern in cold and warm season? Intuitively, you expect that people are more mobile or less mobile based on the temperature and so on. So we could see also that something which happens, the slope change a bit. So people visit closer parks during pandemic in both warm and cold season. So first of all, again, in both seasons, we could still see gravity, but we could see the slope has been changed, and we could see that how it's changed during and comparing data during pandemic and before the pandemic. The other filter we applied, or let's say subsampling that we did to this data set, was that we went further and we classified the data with different socioeconomic groups. What it means, we use SVI, Social Vulnerability Index. So it's considered different factors like economical factors, education, different types of factors, and gives you one index, yeah? And it gives you how vulnerable are those social groups. And then we filter different social groups, let's say, to see that how mobility of them have been changed. And what we came to conclusion was that closer parks become more popular among the least vulnerable visitors. However, in contrast, the most vulnerable visitors have more interest in visiting distant parks. That was interesting. But we didn't have further data, for instance, some questionnaire or whatever, to ask them why they have chose what's. But this is interesting observation, and it can help policymakers either to provide better facilities here and there, to have more equal society and so on. So you have some idea that what could be practical steps to do in this regard. The other things we did was to compare large versus small cities. People who are living in large cities may react differently from those who are living in smaller cities. And that was also interesting. Again, you could see that always we had a robust pattern of gravity. We could always see that. However, the slope was changing. And by changing the slope, we were coming to conclusion. Here, we learned that visitors from smaller cities prefer visiting further distance. Interesting. However, those who are living in the larger cities prefer closer parks. That was, sometimes some observations were not really intuitive for myself, but that was what data was showing. So it's good to see that what is your intuition also living, for instance, in different cities and so on.
Just from small cities, they prefer just traveling a large distance, or they prefer to go to a nice park?
The further data, we didn't have to say that what is nice park or whatever. Then I need one index to say that, okay, so this is a nicer park, or with more facilities or more entertainment facilities, whatever. Then I say that there was the interest. Just for your information, there are other variation of gravity model as well that they consider. For instance, this factor of renormalization depends on the attractiveness, for instance. You know, they include some sort of that, okay, maybe is that. It's not the case for us, but there are some people that are approaching that this way.
Maybe the distance is irrelevant, like what's the nearest, like the sorting, the ranking of the parts should be not much. Might want to compare, no?
No, the point is that
small city, you have
less access to the parks, yeah? So they need to go further to have more parks, whatever.
The closest rather than
But when we say they choose, it means that the pattern comparing to what is compared is during and pre-pandemic. So they had earlier chosen other, so they had options, but they changed, statistically they have changed. So this is important to know. So this is speaking about the slope change, yeah? So change of behavior.
Yeah, Olga, you were basing these conclusions about on the exponent alpha, yeah?
Yes, exactly.
But what I found strange is that you have an alpha smaller than 1.
Yeah.
And so, of course, Washington State is very small, but usually in gravity laws, alpha needs to be larger than 1 because otherwise you have a problem with the normalization. If you sum over all R, it needs to converge. Is that the case that in all cases it's smaller than 1?
I can check it. I don't remember the whole numbers, but I can check it to remember the details of that. But the changes are not so much. That's true. And the main one that I have showed you, yeah, it's less than 1. That's true. But I see your point. Yeah, but I see your point that it may matters also if you look at that from this perspective. That if it's that's true. That's true. Yeah, good point. So. So that's what we have learned from here. And then we went one step further to see that, okay, what else we can learn from this data and how we can get some more information for analyzing this data set. So we wanted to understand also propensity and diversity of the visits. What it means? So it means that we try to visualize or to, let's say, represent the data in different formats, yeah? So the data that we have now, based on that, we build up network. What it means? So I consider that each of the districts that I have is one node. I have a duplicate of that one. The parks also are one node. So I said that how many people from this node are going this node. So I have a matrix, or a network, let's say. So I say that from this node, how many have move to the other one and so on. So it's weighted clearly, yeah? So how many have moved? And then you can calculate out degree and in degree of this, yeah? The out degree, this is the out degree, census block, how many went out to how many different districts. It shows that, for instance, imagine that the people who lives in this district, they chose to go to 20 different districts for the parks, yeah? So that's, the out degree is 20. 20 links went out. And the in degree, it means that how many parks received from different districts, yeah? So I have in degree and out degree of that network. And this color code, it shows that what is the out degree, and the changes during the pandemic, you know? So that's the information you gain here. However, you can go one step further and to find the correlation between different factors to understand how this network representation can give you further information. So I choose the degree census block, and here the degree of the park. So basically this is out degree, this is in degree, and with different factors. Here was social vulnerability index, yeah? And here was visitors and area of the park. I want to see how much they are correlated, how people have chosen that, okay, based on their socioeconomic background or based on the park, how big was that, how many visitors the park had, they chose, for instance, to go on that. Different factors, we found the correlation, but I just bolded here the one that we could learn something from that, yeah? So here you could see the largest correlation. And what it means when you see that, it means that the higher the social vulnerability of an area, the resident of that area exhibit a lower propensity in park visitation. The richer you are somehow, the still you diversify your visits, more or less, yeah, to give you some intuition. The parks in the richer areas of Washington State did not exhibit a significant difference in their visitor diversity also. So it means that as diverse as earlier they had visitors, during pandemic also they kept from different districts, those parks also. They receive the still from. Why this is important? You can imagine that. If you want to strategically choose somewhere to go, you try to avoid to go somewhere that there's higher risk, that people are coming from different areas and so on. So it gives us still some sort of information to policymakers during pandemic that, okay, what they can offer in order to suppress the risk of the interactions and the transmission of the diseases. Yeah? So that's important to know that how things have been changed. So far so good. Just to summarize, we learned that anyway, this gravity law was almost robust everywhere. We could see it. And even though we continue sampling and filtering, again, we could see that. And by change of the slope, we could learn some information how statistically people have changed their mobility pattern in reaction to pandemic. The other part of my talk is focused on how mobility is impacting epidemic. So far, we have seen how pandemic impacted the mobility. Now we're going to go to the other direction to learn that. So this book is named The Big Bang of an Outbreak because by this we have learned that we introduce a framework that by that you can really find the origin of the epidemic. It means that in a space and time to say that when that started. So that's why we named it Big Bang. So that was when and where this started. So let's see that narration from what really was the challenge for us and how we came to this framework. So at the beginning of COVID-19, I was back then in Iran. I was assistant professor in Sharif University back then. And if you remember, so China was the first. And then the second countries were Italy, Iran, and so. So we were the second ones on the row, so we were facing that. So it was really beginning of the pandemic that COVID was a big challenge for us as well. So it's good to learn about that to see what was the main challenge back then for us. So this is map of Iran. So if you want to, this is Caspian Sea, if you want to know geographically where it's located. This is Caspian Sea, Persian Gulf, Oman Sea, and Indian Ocean, and so on, yeah? So here is Tehran, the capital, and population of the whole country is about 83 million. So those Germans do know more or less similar to German population, however, the country is bigger. Tehran is the capital city, and the population is around 15 million, with all suburbs, not only that. And Qom is a relatively small city, and also if you count the province, the whole province is located near Tehran with almost 3 million population. So they are really next to each other. And the largest international airport is Imam Khomeini Airport, which is located between these two cities, Qom and Tehran. But you see that 89 kilometers away from Qom and 55 kilometers away Tehran. So just to know that this is the location of this one. So what was the challenge? So back then, remember, it was February 2020. It was one parliament election, for instance, in Iran was going. So already some reported started that we have the first deaths due to COVID-19. And then it's good to know that Qom also is a city of religious schools. So people have some sort of emotion about that, either positively or negatively, but they have some sort of emotion about that, which I don't enter to the details, but they are not speaking about Qom rationally. This is important to know. And then what was the point that a debate started in the country that why government is not isolating the whole city of Qom and does not stop from the beginning and so on and so on. From our perspective, I had worked before with the data. I was aware about that. Maybe it's already late. Maybe Tehran is already infected. So these types of discussion is out of point. So by it was practical point of view, very important to know that where is the situation right now in Qom and Tehran. And what was the debate in the society was not really rational or scientific point of view makes sense. They were really emotional for different reasons about the things and so on. So that was for us the question, scientific question that, okay, can I figure it out? What is the situation right now in Qom? And what is the situation in Tehran? And what we can do in practice, really, to try not to let it go to another level or try to help the policymakers, let's say. The data sets that we have available was just 2 screenshots. So one screenshot, 23rd of February 2020, was the number of active corona cases. And just remind you, back then, still we didn't have this PCR tests. Yeah, it was not still available. So with different methods, physicians tried to say that, okay, this person has corona and so on. But anyway, they had some sort of diagnostic way to say that it is corona. And so these were the active cases already in different provinces. And this was the daily passenger flow that is averaged over a few days that we had. That's the full mobility based on the mobile data, which is coarse-grained. The whole country mobile data that they had access to that. Another team in math department, actually, they worked on that. They coarse-grained it. I asked them just to give me a matrix of 33 times 33. So they're coarse-grained by provinces, that how many people during the day from that province move to the other province and so on. So that's basically the data I had, yeah? So that's all what I had available. So let's have a flashback to a work of my colleague that they did it earlier and to see what they have learned, yeah? So this is a very nice work and it's quite well visualized. Everyone can get the main idea of that work, yeah? So they have, this work is named The Hidden Geometry of Complex Network-Driven Contagion Phenomena. And what they did is very interesting to know what they did. What kind of data they had? They had empirical data. The first empirical data they had was the mobility network of air traffic worldwide. Yeah? So how many people daily are moving from one airport to the other airport? This data is quite expensive, just to know that. There are some open data. People estimated that by how many flights are going from here and how big is the plane they estimated. However, you have really the actual precise data, which you have to pay. And they had that data. So, so this is the air traffic data they had. The other empirical data that they had was the active cases during, for instance, a time window. So they were estimating, for instance, between 5 days, how many active cases received passengers that they had. They had that pathogen and they received to a new airport and so on. Yeah, and this is the pattern, for instance, you can see. So they had similar data that we have. Yeah, so mobility snapshot and also the active cases, even though the time window was a bit bigger, but this is the source of data. So if you're gonna plot the arrival time of the virus or pathogen, whatever it is, versus geographical distance. This is simulation data. You don't see any pattern. This is for H1N1 data. You don't see any pattern. This is for SARS 2003. You don't see any pattern. But we are physicists, we don't give up. Yeah? We play around to find a pattern from the data. How you can do it? They define something as effective distance rather than geographical distance. And then suddenly you have a pattern. So everything goes on a line. So the geometry, that hidden geometry is a line basically. So that's what they see. But what is the effective distance? What they have defined here. For effective distance, they say that it doesn't matter that where is Hong Kong, where is Sydney. What matters is that how many people are moving between these two nodes. So the probability that someone moves from one node to the other node matters more, and the population that they are located there is matter. Yeah, so that's important. So it's not really the distance, rather that if every day, every hour you have one flight, so these are closer by distance, basically, even though geographically they are not that close, but they are closer to each other. So what they do, this is the flux from M to N, which is normalized. So then you have the probability to move from N to M. And then you have log of that, and 1 minus log of that is the effective distance. So they choose this function intuitively, let's say. Why you have log of something or whatever, yeah? It makes sense you have probability, but why log works, I'm pretty sure they have played around or they have some intuition somewhere that they build up this one, yeah? But this is why they build up. And then they were also, if you go to that paper, you can see that they have discussed this, because when they worked most probably with that data set, they have already seen there are some challenges. And one challenge is about the direct flights and the other. So you know that, so I came from Leipzig to here, I had 2 stops. So how I'm counted here in this framework, yeah? So my final destination was not, was Sydney, was not, for instance, Vienna or Bangkok, where I stop also. So it means that you need some sort of correction somewhere that, okay, it's not necessary just a direct moves from one node to the other node. Rather, you may need to know that the intermediates may play a role also because of such kind of long distance mobility and so on. So they were also aware about that, and you can see they have discussed that. You need somewhere to find the minimum distance there to find out where is that and so on. So basically, here at the end, they have the arrival time versus the effective distance, and then they have the other factors, yeah, which shows you that these are the parameters from the disease itself. So the infection rate, recovery rate, which is a specific for that a specific pathogen and so on. However, they have one free parameters, which is based on the intermediate passes that they need to somehow play around to find the optimized version of that. And they are aware about that. And keep in your mind also, if you remember the first data set I had shown you, the arrival time also was not very precise. It was 5-day window, for instance. So it means that they had 2 freedoms somehow to play around till they can find the perfect geometry of this effective distance. So they were themselves aware about that, and they have played around to find this one in practice and so on. And then they go further. If you want to find the origin place also, so what you do every time, you put one of the nodes as a source to see which one gonna then give you that line. Then you say that one is the origin of the epidemic, yeah? So these methods also help you to do that. However, you can imagine that if you have multi-sources, you cannot detect it with that, yeah? So if you have, just imagine for any reason, so same time you have the pathogen that they start to grow. So then you cannot detect it with that method, also the origin. So far, so good. We applied this to our data. Come back to the challenge that we had for Iranian data set, and it didn't work. So I could not understand either Qom was the origin or Tehran was the origin. I could not say that, okay, which province is the next that's gonna see the pathogen and so on. So you see that the regression is not so high. I could not really have that clean line I expected to see. So either I should clean really to kick out so many nodes because of different reasons to say that, okay, maybe it's not, but still it was not really informative for my case, at least for my data. So we said that, okay, so there are something that we should figure it out what to do. So we started to build up our own approach to understand its dynamic. What we did, again, I emphasize that I only have 2 sources of data, 2 snapshots. One of them is the active cases and given day, and the other one is the mobility pattern, which is coarse-grained between those nodes, let's say. What I can do. Now I define a vector. This vector, the E represents empirical data, so number of infected 1, at empirical time. I emphasize this. You can imagine that the day I know how many people are active, they got it maybe a few days earlier. So that's why I say that is empirical time. It's not the real time they got it or something like that. The later on, this can help me to find out the real time, to estimate the real time that I have. So this is the number of active cases at time t at each province. Province number 1, province number 2, and so on. Now I want to see how this is going to change in the next time step or next day, whatever I have. Yeah? So I say that I have two dynamics. One dynamics is inside the province. The other dynamics is between, how they have moved from one province to the other one. So one is, let's say, intra-population, homogeneous mean field approximation, which I use SIR dynamic for that. And the other one is in a meta-population. You have coarse-grained the data. You say how many population are moving from one province to the other one. And it's interpopulation between different populations. So how we can go further? For SIR dynamics, I believe you have seen the equation so far. At least during the pandemic, everyone had seen this and so on. So I say that number of infected one, how going to be changed? The new infected one with rate of beta going to be infected. These are the susceptible one and in neighborhood of the infected one. And some going to recover with this rate. So basically, I have two terms. This is for SIR dynamic. The next one that I have is that I want to see that how many infected one I have at node I. So some went out. I don't care where they went. I just say that with probability of the P, this is the passengers of that day overall. So if they are the node I who is sick may go out, go somewhere else. And some others come in, but it's important from where they are coming, while they may have already more infection or whatever. So then I see how many IJs with that probability came to me, to that node. So I have two terms also here. So it means that now this is my equation. I have two terms. So one is the SIR dynamics, the other one is between the provinces or the mobility that I have. And then I want to see what I can. So far, everything is exact. Yeah, I have not, but I cannot solve that equation. At the beginning of dynamic, really early stage, I can approximate number of susceptible with the population of that province. So it's not so many. So imagine that when population is 15 million, only 1 people or 10 people are infected. So I can still say number of susceptibles is more or less 15 million. So I can approximate it. What it means, if I replace S with N, which I know the exact number of N, then look, you know this equation, yeah? You have I here. Every term also have I. Well-known differential equation. So that's the solution of that. So basically you have an operator. If you start from initial condition, with that operator at time t, you know how many infected you have. And then here, basically with that operator, you can have the Taylor expansion of that operator. And if you have the Taylor expansion, what it means that you know the role of intermediate passes as well. If you cut it off, the first term shows you the direct moves. The second term shows you that you went to another and then you move to the other provinces and higher one. And also by this, if you know where you put the cutoff, you can define the error bar. You know how precise you are estimating also the cases also. So you have some sort of error bar also based on this framework. So basically, this is the operator B that we have. On diagonal terms, you have the terms related to that specific disease, to that specific pathogen. The infection rate and the recovery rate. So you go to the pattern that you have at the earliest stage, you fit it, you find that parameter, you put in the diagonal of that one. Non-diagonal terms are the passenger probability moving from one province to the other province, basically. So that's basically your operator B, and that means that if you have the Taylor expansion. You had a question, no? Okay. So this gives you the picture that what you are doing, and you don't need to tune any parameter or what's going on. And for this operator B, we used the name of one of ancient Persian myths who was in charge of disease spreading and killing. So we say that this is some sort of, that means to kill further, goes further. So the further you apply, the more you kill. Basically, this is the idea from the Asian mythology. So then we started to answer those questions that we had originally. We want to figure it out where that epidemic began. Now I have a good framework for that. I can define the basis of the space. So if I say M, for instance, is 0001, it means that province had only one single infected one at time 0. Now, if I have the snapshot at time t, I project it to all bases. And then I see that which one gives you the biggest one, then I say that that was the origin. It started from there. That's why I see that, yeah? And this means that you can also find the multi-sources, because you can see that it's the case. So look, if I give you the data, there's a snapshot that I had from the active cases in the 5th day of the corona case in Iran, this is what you can see. And you can now interpret it differently. So based on that, definitely we can say the pathogen came to Iran via that airport, not other airports. So that was basically the source. However, it means that about 45% of passengers who had already the pathogen, they moved to Qom, and about 20% of them, they went to Tehran. So it means that Qom and Tehran were infected, but in a different percentage, let's say. Yeah? So that's what you can see. And you have error bars also based on the cutoffs that we have discussed, that you can say that, okay, how much error I have for this estimation, for instance. You can do that for day 10 or 20, whatever snapshots that I have, to be sure. You can see when you come to the Dente, you change that one. So the Tehran was more infected if you rely on that one. So it's very important to remind yourself that after I approximated S with N, it means that this approximation is valid just in a very early stage. Yeah? So there is a moment that then you cannot figure it out. You cannot use anymore this approximation and so on. So just the really early days can give you that picture, and they can help you to figure it out where the epidemic began. So anyway, one thing is very clear. Tehran and Qom were infected. However, the percentage based on different data set that you have, you can say it was varying. That's important. We did similar things for US data also, and we could see, so for instance, Washington, MI is Miami, am I right? Michigan, yeah? Michigan and so on. So you can see also based on different snapshots that you had, so you can see that what has happened there also in the US. The next question is that we know the data, the day that we are looking is not the real data. At least, for instance, for corona, we knew that almost 14 days delay or something like that, we have delay for the cases we could actively see. So it means that the pathogen came earlier, but how many days earlier? You need the correction. How you find out that correction? Now you know where was the origin and how much was the percentage. So you build up based on the theory you had, what you expected to happen in theory for the number of infected one. You're gonna find the difference between the empirical data and see that which one gives you the minimum. And based on that, you're gonna find out the time correction. When you have the minimum difference between the theory and empirical data, after you figured out where that belongs. And then you have the correction. As you can see here is about the T star, or that correction. For Iran is about 21 days. For US similarly, you have That one. So that means that the correction factor that you need for time is like that. And now, so we learned that, okay, with this framework, not only we can say that where it began, but also we could say when that began. And now we went to the next question, that we want to say that how it went further, or what is the next step, which provinces I expect to see something. This is also important to know. You imagine that at the beginning they wanted to put whole countries on blackdown. Yeah? However, you know that that's not economical point of view, it might not make sense. So still, that area is so far away, they have not received any pathogen. Why they should stop working, or, you know? So if you know when it's gonna arrive, so you're gonna prepare yourself better and so on. So it can give you a better idea for policymakers how to do things and so on. So now we change the perspective. So do you remember in that work, Dirk and Dirk, basically they were showing us that by effective distance you can change, but they were looking at arrival time. Here, I'm not caring of the arrival time, I'm looking at the time. You remember I have two dynamics. One dynamics is the SIR dynamics, basically inside the population. The other dynamics is the mobility that I have. So I'm looking at the time that this SIR dynamics take over. And then if it's fast enough, then it does not matter how many ill people are gonna receive anymore, because the dynamic itself inside is fast enough, so those are not matter anymore. So that time matters. Overtaking time matters. So I wanna find out which time these two dynamics gonna be more or less equal. So then I use the Taylor expansion of the I that I had. So this is the time that you have, and you go one step further. So if you want to see the effective distance, you can define now a new effective distance based on that. And if you define that effective distance, that means that if you look at effective distance that we defined versus overtaking time with one factor, you're gonna have a line. But if I plot D versus PT, I have a line with a universal slope even. So the slope also is 1 and universal. So this is basically what we could have with this new framework and new definitions of the effective distance and the time. So now I plot effective distance versus PT. So no matter where is the source, if the source is Qom, so the data sets I have is green. If the source is the Tehran, so you have the gray one. Anyway, I have one line with a slope of 1. If I look for the US, it's similar. If the source is Washington or Michigan, so at the end I have this line, and that's with universal slope. So this is effective distance versus overtaking time. This is simulated data. However, empirical mobility data were used, but for the active cases was simulated. But the next plot shows that every data was empirical data. The mobility data was empirical, and also the active cases that we had. So we can confirm for COVID-19 in Iran, we had that line. For COVID-19 in US, we had that line. And also we could check it for H1N1 in the world also, we have that line. So what we learned, it means that with this definition of the effective distance and time, we have a universal geometry, which is the line of the spread. We know that which node is the next one that's gonna receive. And does not matter what is the mobility. Either is Iran, which has different mobility pattern than US or worldwide, different scales even, yeah? Because everything was coming to that definition of effective distance, and it doesn't matter what was the pathogen. It was COVID-19 or H1N1. So I could see a universal pattern with the slope also here. So to summarize this part as well, so we could figure it out what is the big bang of an epidemic, which means that where and when that began, and then how it's gonna spreading with this framework. And the advantage of this is that we only need 2 snapshots, and we can introduce the cutoff errors. We know that what is the error of our estimation to recognize the source of the epidemic. And also we can detect multi-sources, which was not the case for earlier studies. So this was also the second part. I would like to thank also my students and colleagues. So Zahra back then was a bachelor student. She was quite good, really. And Yazdan was behind the estimation of the Big Bang. He is really amazingly good in such kind of mathematical frameworks and so on. So, and Amin also was my student as well, and other colleagues. So this was also thanking to my colleagues, and thank you for your attention.